Hello and good morning, everyone. I'm going to have an interesting little walk through kind of the last 20 years or so of my career. And the one thing I found interesting in the last year particularly is that we keep seeing it's the 20th birthday of Java. Has anyone got confused about what the actual date is? I am. I keep seeing things, it's the 20th birthday, but when was it? Well, kind of interestingly, 20 years ago, it was out in a sort of beta or alpha form. We'll see quite soon that it was really 1996 is our 20th birthday if we look at our 1.0 release. So what am I going to cover here? I want to go through a little bit of the history of Java to sort of see how it's sort of gone over time, how performance has been affected. I'm going to kind of look at a number of other things around like how we design software, how we have seen hardware evolve, and how we see sort of culture evolve over this time. And a lot of it's kind of this, what I've sort of observed being in this industry. I started professionally programming C++ in 1992, and I started using Java, kind of looking at it around 95 and done my first commercial project in 96. So I've seen the two go side by side over the time, and it's been a kind of interesting history for me and how it's gone. So let's kind of go forward here, and we'll start with the brief history of Java. So if we look at the kind of timeline of what happened, sort of right up to sort of modern times, we started right back off in 1996. But let's go back and look at this and how did it actually start. Well, if you actually go back to 1990, and in December of 1990, Patrick Norton, Mike Sheraton, and James Gosling were involved in a thing called the Green Project to produce something that ended up in Java. But I find something really, really interesting. This photograph was taken in the fall of 1991. Now remember, 1991, Java did not exist. Look at James's t-shirt. 1991. I had to dig up some history for this because Java actually started off being called Oak. And in the early days, what they were trying to do was build a piece of software for this. Kind of think early iPhone, really clunky and big. This is the Star 7, and this is what Java was originally invented for. It was called Oak because there was an oak tree outside James Gosling's office, and he named it after that. Turns out there was some sort of issues with rights around that name, and it got renamed as Java later. But clearly you could see from the t-shirt, James had an obsession with Java from earlier than that. So, anyone seen this little guy, Duke? He's been around for a long time. Guess what he originally was? On this thing, he was kind of clippy. Like that little annoying thing you find in Windows going, "Can I help you out?" That's what Duke was. Duke was the clippy of this day. Kind of interesting guy. And they also looked at how do they make software to run on things like set-top boxes. Interesting times. So how did it perform? What was my first experiences with Java? Was it this nice, fast, lean thing that went really quickly? No. It was a bit more of an asthmatic dog. Very, very slow in many ways in how it performed. But that's it. Everything has a beginning. We have to start somewhere. So kind of moving forward, you can kind of see where this really started. So January 23rd, 1996 was Java 1.0 release. And so we probably should celebrate next year, really, when it's the 20th birthday. But as we do and go forward, in this era, one of the things that really stood out was Netscape Navigator with 2.0 decided to support applets in the browser. This was a big step forward and really helped Java come onto the map. IE 3 followed that in those days. So interesting things. As a C++ programmer, whenever I first seen Java, the thing that amazed me in it quite quickly was this ability to manage memory, the automatic memory management. Very useful feature. So I didn't have to worry about garbage. I spent a lot of my time chasing down bugs that were caused with pointers or dereferencing the wrong thing. I learned to do things like overload new and delete to put things in different parts of the heap so they didn't crash. But with Java, I didn't have to worry about that. But we started discovering that as soon as you used it in any anger, we had problems. And part of the problems was the garbage collector just wasn't good enough, so we ended up doing object pooling. And this is like the start of this in the early days. But we had some cool things. Like all of a sudden, I could write really rich user interfaces and deploy them hot. Now, this was a big deal. If you were writing software in the early 90s, to install the software on client machines involved shipping floppy drives out, usually a big stack of floppy drives, and all sorts of complicated ways of doing this. Like, we're just in such a nice time now where we can just, over the web, have a user interface available. But Java was the first way we could do this. It was really nice. And we could do things like do multi-threaded programming on Windows 3.11. This was cooperative multitasking. We didn't have the ability to multitask like we can do today. And for me, this was really cool because I had written a Windows scheduler that did very basic preemption back in those days that sat on top of Windows 3.11 so people could get stock market feeds, and that could be running in the background whilst they were looking at their Word document. So this is nice, big, really cool things. And we kind of go forward, and then we get 1.2. Things start to change, and Symantec and Microsoft went in with trying to do JITs. Some started off thinking, oh, they'll build this really great thing. And then Microsoft started getting involved, and there's a kind of dark side that sort of went forward from here. But we started getting JITs. Now, whenever we used JITs in these early days, this was a way to make our software a lot faster. And we were encouraged to use the Symantec JIT. If you used that one in those days, you pretty much guaranteed your program was going to crash very quickly. It just wasn't that usable. The actual dark secret that was around at the time that Sun didn't want to talk about was the Microsoft JIT was really good. In fact, the Microsoft VM was by far the best one in the early days. Because Microsoft had a little bit of a history of this. They'd been doing P-code with Visual Basic and had a lot of experience and could actually make this work quite well. And not only was that, it actually scaled well. It was the first JIT that actually had native pointers. We didn't have to go through proxies to get to our objects. So this was all quite fast, quite usable, but you had to run it on Windows to get the benefits out of it. But now we had this other interesting thing because we had this war of platforms, and I'll talk about this a bit more later. We could actually have GUIs that run across these different platforms with Java. We step forward a bit further, and we come forward to having 1.3. At this stage, the big step forward was the generational garbage collector and servlets, which I'll mention. Generational garbage collector was probably the first case of where we could really use a garbage collector and benefit from it and step away from object pooling. So I kind of said this is about learning and unlearning. We learned that object pooling was the thing to do. We then realized it wasn't a good thing, it was a bad thing, and we had to stop doing it and move forward. But I kind of found this a crazy time. We were dealing directly with Sun Microsystems. I was based in the UK, but it felt like the executives were smoking dope in San Francisco. They kept coming up with these crazy ideas. One of them was, let's design a chip to run Java. And they built this thing. It was horribly slow. It was a real problem. Never went anywhere, never came to fruition. You can still get the specs and run this on an FPGA if you want to. But they built this little beauty, the Java Station. Is anybody here old enough to have programmed on one of these? Oh, there's a few. Can you remember how slow it was? It was the most disgustingly slow platform I think I've ever worked on. This was worse than programming on sort of Z80 and VIC-20s in the 1980s. And this is supposed to be an era of reasonable hardware. It was just a horribly, horribly slow and unusable thing. And then on top of that, it had a browser called Hot Java. And it was not hot. The only thing that was hot about it was the CPU trying to keep up with running this software. Yet these things got peddled to banks and, they were used everywhere, terrible machines. But then there was a real surprise. For me, this was the turning point. This is what happened that made Java successful, and that was servlets. So all of the history of Java and everything that happened, we were programming CGI, we were writing Perl scripts, writing C. You had to start a process for everything, open a new connection to the database, respond to a request, shut that all down, start again. This wasn't scaling. Then all of a sudden we have servlets. We could have a thread pool. We could hold connections open to the database. And all of a sudden this language that was used for applets sort of started being used on the server side and started being used in huge quantities. And I think this is the inflection point, and without servlets, we would not have Java today. It would not have become what it becomes. So it's funny how surprises start out. We think something's going to be useful, but then the truth to what makes it useful is really very different. So we kind of go forward from here. Now we've just passed the turn of the century. We started getting some really interesting competition. The hotspot compiler comes along at the stage. We get JRocket. We start getting really quite good VMs that are quite fast. Fast enough that you were seriously considering, I can use Java rather than C++. And actually it became the first choice in many cases because the development cycle was nice and short. It had good tooling. This was great. This guy got hired by Sun just a bit before that, and it's one of the reasons we ended up with the fast JIT compiler, Cliff Click. He comes along and introduced the whole concept of graph theory and how we use that to create an optimizing JIT. This was giving us really quite good, fast code for the time. So Java's this nice, fast thing. It's starting to be usable. I'm feeling happy about using this rather than C++. My days are now spent doing more Java than C++. This is great. Then we get EJB. So we've got this nice, fast platform, and what do? We slow it down. We slow it down a lot with this abomination. Like, if anybody remembers things like EJB Home was the way you created an object. It didn't even have a virtual constructor, so we had to use these horrible static methods to make it usable at any sort of speed. As a result, it was untestable. Yeah, major design flaw. So we're back to this again. We got fast, then we're slow. We move forward again. Things are getting quite interesting around 1.4, particularly on Linux. We get things like the Blackdown JDK, which had native support for epoll. We'd be running very fast containers that were running servlets, servicing lots of web requests, and we got NIO. But then the world kind of crashed. The dot-com bubble burst. And as a result, if you were working at this time, I found it great because I've done 5 startups in 12 years. And it was really easy to go buy hardware at this time because you would not go buy new hardware. You went to a liquidation sale where companies had gone out of business, and you could buy these things really, really cheap. The cool thing about them is they had multiple processors inside them. So we were running our first Java on genuine multiprocessor systems. That was a commodity type of hardware. Before that, any multiprocessor programming I was doing was on things like Dynix and very large Solaris boxes. But what started showing up from this was, as we were doing 1.4 at this time, we started realizing there was bugs. There was bugs where after a constructor, you would see an object was not in a properly initialized state. Lots of people started reporting these things on the web and wondering, well, what's going on? This becomes an interesting problem. As a result, we got a nice body of work that went forward, and then with Java 1.5, we got a memory model. And so this was a kind of very interesting time. Well, with 1.5, we got that memory model. We also got some very cool stuff in Java util concurrent. We got lots of other improvements in the VM. 5 was a real growing up phase, I think, in Java. We got generics and lots of other stuff. Like, I actually think things like enums was a great step forward, especially that we could use them polymorphically and design well. But it was just around this stage, Herb Sutter decided to write an essay. And he famously said, the free lunch is over. And what he was pointing out is, we are no longer going to be getting faster processors. Clock speed's going to stay about the same. Well, since then, we have got faster processors, but per core, they have not been leaping forward at the way they were before. So things started to fundamentally change in how we programmed. And around this stage, I had another little sidestep into working on mobile phones. Jet2ME came along. And this was a very different world where I got used to working on these really nice fast servers. Then I started working on mobile phones, and then through a weird twist of fate, working on cryptography on mobile phones because providers in the UK removed all of the root certificates from our browsers, and we had to deal with this by doing the cryptography ourselves. So we had to get cryptographic experts in place, but then how do we make this perform on a tiny little processor using a version of Java that doesn't even support floating point arithmetic? So we were back to this again. And this seems to be the story of my career dealing with Java. Every time it gets better, something comes along and makes it horribly slow again. So all the stuff that's old is new again. You have to do all of the same things. But what happened to EJB? This is kind of an interesting thing. Well, we got a savior at that time. where Spring came along and made EJB a whole lot easier to deal with. It made it testable, made it much lighter. This was kind of another nice step forward. So we got free of doing this at this stage. We then moved forward to Java 6. We got some cool stuff. We got things like escape analysis, register allocation, improvements to how we do locks. Although escape analysis always was one of those things that sort of overpromised and underdelivered, it's kind of getting a bit better now, but it's never been the great thing it promised to be. Then we ended up with Sun being sold. They got into difficulty. They courted IBM for a while. Oracle went to buy them. How did we feel about that? What was going to happen to our beloved Java? Well, actually, I don't think it turned out that bad. Technically, it's been a great step forward. We started getting progress. What's going to happen with the community? Who knows? We'll see where it goes. Now, what happened to Spring? So we've moved forward. Spring was this thing that got nice and light and fast. And then, guess what happened to Spring? Same thing. We ended up in this sort of era of bloatware. Everything turned into bloatware. And we got great things like Hibernate. Come on, really, is SQL that hard? We just do this really, really stupid stuff where we keep going in these circles of slowing stuff down, putting in layers of abstractions that are completely inappropriate. Like, let's go back to what abstraction really means. Like, Dijkstra in 1972 in his Turing talked about abstraction is a way we make things more precise, not more vague. As a result, we've got things like the law of leaky abstractions from Joel Spolsky, where we actually do an abstraction wrong. Let's do this better. Let's learn and use technology to do it the right way. But we had some big hardware changes at this time. Things like AMD came along with hypertransport. All of a sudden, we had much, much more significant servers, but they introduced this thing called NUMA, non-uniform memory architecture, and this had a big impact on how we're writing software. Unfortunately, most people haven't even realized this impact's occurred, and that's nearly 10 years ago now. We also had the advent of high-frequency trading, and this moved things forward at a rate that had just never really been seen before in our industry. We started realizing that now with applications, milliseconds begin to matter. Then it went down to microseconds. We're trading on latency arbitrage really, really fast. We had to do it right from the start. So when a market opens, there's no time to warm up. You had to be fast straight away. If you're running Java competing with C++, this was a difficult time. And also, it's kind of a really interesting problem where these markets are quiet for a while, then they burst frantically with activity, and you have to be able to react really quickly whenever that happens. So this pushed Java to the extreme, and we started doing crazy stuff with it to make it work and compete against the alternatives. And we didn't just do this for the hell of it, because if you are slow or you get this stuff wrong, you lose massive amounts of money. It's effectively like being at war. Companies go out of business if you don't do this right. And it pushed forward Java, it pushed forward technology. The thing that really amazed me was how much it pushed forward networking. We would not have the quality of networking we have today without high-frequency trading. Our switches, our routers, our network cards, our network stacks, they can pump data at high rates at really, really low latency, all driven by high-frequency trading. So we've kind of benefited from that in an interesting way. It shows up all of the weaknesses in what we do. We also started noticing through this period that garbage collection has raised its ugly head again, because we're running with bigger heaps, we're trying to be very responsive, but garbage collection just seems to keep getting in the way. It keeps coming in cycles. We were also told in the early 90s that this memory wall was looming. In fact, there's a paper written in 1994 on this. But the garbage collection kind of has been hiding this for a while. Now when you start dealing with slightly better garbage collectors, this is becoming an issue too. We've got servers now with terabytes of memory, but we can't really use them properly for your average applications. We need to know so much more about how we access this memory. We also start seeing, as we get into this very multi-core world, that programming with shared memory using locks starts to become a major issue. I get to measure a lot of real-world systems, and you see that loads of applications are spending so much time idle where threads are entangled with each other, where you're waiting on threads sort of coming to do things inside the JVM, and so you're limiting throughput. And those things that it's trying to do to the JVM is getting things to save point. There's a number of things our VM must do with every single thread in the JVM stopped. Now, as you get more and more cores, getting all of those threads to that stop point starts to get slower. Getting them all started again starts to be a big issue as well, and the resulting cache pollution is huge. And we're just not looking at this. So some friends of mine who work in the space, we all kind of jointly joke that VM engineers, if they have to put another save point in, they should have to sacrifice their firstborn. It's probably a bit extreme, but maybe have a nice big financial penalty because these things really matter. So now we're on to 1.7. We start getting really cool stuff like tiered compilation, compressed pointers, G1. It's all going forward nicely. Then we get the G1 garbage collectors, a kind of interesting step forward. I'm really surprised there wasn't more effort put into CMS because CMS wasn't that bad, but it just didn't seem to get any love and it didn't move forward. The real standout thing for me is how complicated setting up some of the stuff is. So here's a command that will let you print out all of the flags that you can send into the JDK. Let's pump it to word count and count the number of lines. You get 820 on Linux on the latest version of Java 8. This is far too many parameters. No one can really understand and work with this, and the majority of those are to do with garbage collection. So in some ways, like Java is supposed to be this easy to work with environment, yet some of the config is very, very difficult. It kind of often leads us to a fork in the road at this stage, where the only answer I can see from garbage collection perspective on large heaps, where you've got high throughputs or low latency, is Azul. We need to have much more better approaches in their standard JDKs than this. Like, they have shown the way to what's possible. Let's see others do this sort of thing and do it better. Because this is the alternative. People go off heap when they've got big memory or high memory requirements because it's the only real alternative. We don't want to do this, but let's have a better alternative. We also get things like fork join. This comes along. It's a kind of interesting complexity in how we deal with stuff. So we're getting these interesting steps forward. While we're getting them, can we make use of them? Because has anybody ever tried to debug or profile a large fork join application? It's a bit of a nightmare. And they talk about Java is the place for sort of simple Play-Doh programming. Not when you start playing with these sorts of things. It's incredibly complex. You're back into this, like, what is going on? Too difficult, too complicated. So let's move on. Java 8, how's it looking now? Well, we're getting lots of nice refinements. It's becoming a very mature platform. It's becoming nice and predictable in how it works, and we're getting some really great tooling around it. Lambdas was the kind of nice step forward of this release. It kind of really does improve the programming model. I'm doing a lot of Java 8 programming now. I'm enjoying writing with Lambdas. Yeah, it's a 50-year-old technology and we eventually got it, but it does help. But there's some implications to how it works in Java. I'm starting to see it taking much longer for an application to warm up and become fast in the first place because it doesn't instantly respond with these. We also have Java streams. So this whole thing, like, we brought in things like Hibernate because we don't want to deal with databases. Well, we're fundamentally dealing with set theory at that stage. And you bring in streams, set theory has come back. So we spend years trying to avoid learning databases, which is fundamentally about learning set theory. Then we introduce streams, which is learning set theory anyway. It seems kind of crazy. But these are nice. It's nice and elegant. It's a great way to program for some stuff. Just beware of parallel streams. So just adding that one little word to how you go and start dealing with streams can unleash a whole pile of quite scary things and poor performance into your application. So you have to be wary and not just use this. I'm finding this is also the era of measurement. We're getting some really good tools, like Java Mission Control is a huge step forward for how we monitor and deal with our VMs. Telemetry being a first-class thing is so important. We need to take this more seriously. People are measuring MFRs. We've got great profiling tools, great benchmarking tools like JMH now. So it's all moving forward in a kind of nice way. And occasionally Java does the odd weird thing. It tries to be a hipster. I don't know if you've got the sort of hipster concept here in Russia, but within the UK and the US, there's this whole thing about sort of trying to be cool, like trying to join the JavaScript kids, but do we really need JavaScript? Like all the engineering effort to run JavaScript? I'm not seeing the call for it anywhere in any enterprise programming. So let's see, are we spending our effort where we need to be spending our effort? So that's a kind of quick last 20 years of Java, some of the stuff I've been involved with. Now let's kind of get on with the main story. What's been happening over the time, so I'm kind of grouping into 3 eras of what I've been dealing with. The 90s was so much about GUIs. And why it was so much about GUIs is we couldn't deploy applications very easily. We didn't have the web like we have it today. It did exist then, but it wasn't what we have now. So many of us who wrote a lot of code in the 1990s wrote lots of GUIs. We had to deal with lots of different windowing systems. And the number of times I've had to write an owner draw list box. If you'd done Windows 3.11 programming, there was no multi-column list boxes. You had to do that all from scratch yourself. Java came along, we built those sorts of things ourselves before we got the later versions of Spring. JavaScript came along, we built all this sort of stuff again. We were constantly building these things over and over again. The shocking thing for me was these were all solved problems, and every time a new group came back to it, they didn't look at the history. They didn't read any of the past work, any of the design principles, and just invented it all from scratch again. And as a result, it tended not to perform. It was a bit clunky, but there's better ways of doing stuff. But this era was fascinating. We had the bottle of the desktop. We had Windows 3.11, and we also had OS/2 Warp. IBM had successfully sold OS/2 Warp into many finance organizations, and it was doing quite well, so we often had to deploy for both of these platforms. Well, the only choices we had to go for all 3, or for all 2 of those, was probably 3 different options here. We could write native apps, but they wouldn't port very easily, so we were either doing Visual Basic, Smalltalk, or Java. I found an interesting thing in this time, and that was which is going to be the best performance. There's lots of arguments about which one of these platforms performed better, which ones were better to work with, and I got involved in many competitions to build the fastest and best platforms. This happened a lot in financial trading systems, and the one thing that was common over and over again was not the technology, but who's your team. The people made more of a difference than the technology did. Like, if you ever build great GUIs, one thing I would recommend is get a games developer and put the games developer on your team. One of the things they're really good at is they build user interfaces that are understandable. Because one of their beliefs is people don't even read the manual, so you've got to make it of high affordance, high understandability in how it works. And they also can do some quite elegant designs. We also realized that one of the really key things to making software very usable was, what is the communications mechanism? You can't really ignore that. You can't say you're a GUI developer and not understand how you communicate with the server. The patterns of interaction really matter. Writing stuff that's very asynchronous makes a huge difference because you've got long latencies to the server. One example we had is we were building this insurance application, and we decided that 2 seconds was our maximum response time, so we split. There's a budget. 1 second was given to the client, and 1 second to the mainframe to do the processing. We agreed an interface. We went separately. We built both bits, and then we plugged it together. And each of the bits on their own were well under 1 second in response time. When we plugged them together, we couldn't even get close to the 2 seconds. After a number of profiling exercises, we discovered all of our additional latency was in the communications. We were using MQ series to talk from our clients to the mainframe, and discovered that this layer was so slow and also such poor patterns in it, we ended up reverse engineering the wire protocol and doing our own client to talk to the mainframe to get back on time. So you got to be really careful. Like, we're talking about, are you front end, are you back end developer? Sometimes the biggest wins are in the interfaces between the 2 of them. And users really love responsive systems. I keep people saying it's not fast enough, or it is fast enough, or whatever. One of the things that I loved to do in that era, when I was writing software for call centers, I would go and do the job of the people who would be using the software. So you use the software yourself. Get used to it. We would sit in the call centers. We would eat our own dog food. We would use the software ourselves and see what it's like and see what the experience people were having. And you start realizing these people love responsive systems. If they're slow and clunky, they can't do their jobs. They get frustrated. It's not a good experience. Kind of move forward from that, we had the explosion of what became the early big data era. I happened to be working on very large product catalogs. People like Conrad, Hilti, ABB, RS Components. These people had catalogs, and you printed them out, were like this high off the floor. They're talking about millions of products with lots of attributes and lots of multimedia images. How do you index that? How do you deal with it? It's a kind of interesting problem. So typically what you have is you've got to ingest all of that data. You've got to store it somehow. You've got to be able to export it in multi-forms because you're going to websites, procurement systems, internal logistics, ERP, all of that stuff. And you've got to be able to index it and sort it and search it. Well, what I found is virtually every one of our competitors, whenever we built this software, used an ORM approach. They dealt with these incredibly complex data sets using ORMs, and in every case, it was a complete failure. These things were taking far too long, like taking an entire night to load data to have it ready for the next day. This had users in fear, whereby if the job failed during the night, the next day, they weren't able to run their data. They weren't able to do anything about it. We worked on this in different ways. We kept the software for the middle tier separate from how we interacted with the database, with a very clear concern separation around the design. We dealt with it using set theory, not ORMs. So use databases for what they're good at, use sort of other object-oriented languages for what they're good at, interfaced in a clean way. We were processing these same catalogs in like 10 to 12 minutes as opposed to all night. Now, not only was it just that this is better from a faster perspective, what was really good was the users were no longer afraid. Because they were afraid before, if they had a run and it crashed, the result of the crash meant that they could not work the next day. Now they could run all of the data, they could make a mistake, they could then rerun the whole thing again and take the fear out of it. So performance really enabled them to do things they weren't able to do before. I kind of also learned during this era that immutable data really matters. I worked with a great guy on this project who used to say, you're not allowed to use the update statement when you're writing SQL. And initially I was a bit surprised by this because everybody else does. What's he saying that's different? And what he was pointing out is that if you use the update statement, you end up rewriting history. When you've got history overwritten, you can't go back and fix problems. You can't fix the bugs that you've just created because you've lost the data. You have to go to tape. And actually, a bit of a tip, I have 3 times in my career had to go to backup tape to resolve systems that got corrupted. In all 3 cases, the backup tapes were also corrupt. Do not rely on tape as a means of going back in history. It's really, really scary if you have to do that. If you just do insert only, so you keep appending to a database, you don't lose the history. If you make a mistake, you can remove the data that you've just added. You haven't broken everything that's gone before. You can also do things like you can query our databases concurrently with updates happening, these inserts that are happening, because they're happening at the end of the table and beyond. They're not happening in the table making changes. So you're always getting a read consistent view. And they work much better with how storage works, which I'll come on to. Set theory itself is also really cool. It's kind of good that we're now getting it with Java streams, but if you're going to use a database, learn how the database actually works and use it correctly. Don't learn how an ORM works and use that as a means of talking to it, because it's a really imperfect abstraction and you don't get the best out of it. I also discovered through this era that JDBC drivers really suck. So if you're pumping huge amounts of data and you've well-tuned and a well-optimized application, what you start to realize quite quickly that the majority of your time is actually spent in the JDBC driver itself. Going back to these days, so you went back to about 2005, 2006, most of the JDBC drivers copied data 5-6 times from you submitting the query till it eventually going onto the wire. All this layering and conversion made it really, really slow and not very useful. Also, when you start dealing with large data sets, a really important thing is how we go through the data, and streaming the data really matters. And what do I mean by streaming the data? Keep the memory footprint constant, stream over the data, and do computation as you go. This is a really nice way of working. Like, we have to deal a lot with like JSON, XML, all sorts of interesting protocols. And if you look at something like XML, SAX-based interfaces are much nicer than DOM-based interfaces because we can keep that nice flat memory profile as we work through the data. We stream it in, we deal with it, and we keep going. Now, APIs make the biggest difference to performance from what I've seen in this space. And here's a really simple example. So as I'm getting an entity tag come through in XML, so when I get the body of the tag, I'm going to get a number of characters. I'm going to get a number of callbacks as I see characters, and it's going to give me a character array with a start and a length for what's going to be handed to me. This works really nice in that it doesn't matter how the data, it can keep coming to me in chunks, keeps it really nice flat memory profile. Then in the same API, we've got this, where you get a start and end element, and we get things like strings here. So even though most people don't even care about the queue name, you end up instantiating a string because of the API. And it's not a case of why doesn't it just hand you the characters with the offset and the length at that point? Well, you could make an argument it becomes easier to use. Well, that's absolutely fine. Well, then how about we design for composability? You offer the base API that has the characters with the offset and the length. You then wrap that in another API that will make it more usable for people who want that hands you a string. But people get the choice. You can compose, you get the choice. This is good design. We seem to just jump to this far end of not giving people the choice, and even worse, mixing design patterns in the same class. And here's another really simple example. String split, I think, is one of the best examples of one of the worst pieces of API design. So we want to split a string and we want to give it a regex. Seems quite simple, and I'll return a list of tokens. Now think about what this means for implication. It limits the implementation so drastically because I'm going to split the string, so I have to have the whole string in memory. I'm then going to go through the string trying to find tokens. I don't know how many tokens I'm going to get, so I need to allocate some structure in advance that's dynamic. I'm going to store all of the tokens in that structure. And then at the end, I need to work out how many tokens I have, allocate in another array, copy that all to the other array, and return it. And then that array is probably not what I want because I'm probably going to do something with it like work out the sync set of tokens, work out an ordered list, do something interesting from another set theory perspective. I've ended up with far too much memory and it's all fixed in size. How about if you just change the API to do something simple like that? Rather than returning the array, return an iterable. And now I can just iterate through them. I'm now in control. You give control to the user of that. It keeps a nice flat memory profile. You don't need to allocate anything internally. And it composes much better into other things. So that's just one simple example. Another way you could do it is you could pass in the regex and also pass in the destination collection into which things are going to go. Now I can actually take control from the outside. I can pass in a set if I want a distinct list of tokens. I can pass in whatever collection I want because I know what I'm going to be doing with it. You give the caller the choice. And I think this is really important in design, not just from performance, but also from just a nice usability perspective, is you give the caller the choice. This was always a C-based principle. Like, as a C programmer, when I started seeing frameworks appear in Java, and the first framework that I seen that had the logging in the framework, I was just horrified. C programmers do not put logging into the framework. You return stuff out through return codes, you provide callback functions to say what's happened, and you give the caller the choice for what they do with this. We kind of impose ways of working with Java onto other people where if we change it around, we actually make more composable designs, more flexible designs, but also faster designs in how they work. So subtle little things. I think if there's one tip to take away on performance, forget all of the really clever bit twiddling. API design means more for performance than anything else in a large-scale application to get things right. And I've just seen this repeated over and over again in history. So Let's go forward. Let's look at transaction processing. Did things change any in that era? Well, I happened to work at two quite interesting companies during this era, where I was at Betfair, which is the world's largest sports betting exchange. Now, what do I mean by large at that stage? It's good to quantify. Betfair seen more trades per day than all the European financial exchanges combined times 2. Sports betting is massive. It's kind of one of these untalked about things that's really, really huge. So it's a kind of interesting financial era, but it's kind of off to the side. So you get this great, really, really interesting performance problems that are in there. And one of the things that was, I thought, done very well there, put in place way before I joined, was the telemetry around measuring the performance of the system. So one of the concepts they had was this of a bad bet. Any user transaction that took greater than 1 second had to be investigated. Why did that take greater than 1 second? And you find out so much about your systems when you've got that as part of your culture. You find that your systems are badly tuned. You find out that GC's not set up correctly. You find that you've chosen the wrong algorithms. All of these sorts of things get found out by doing that sort of telemetry in production. And it may be 1 second, it may be 10 seconds, it may be 10 microseconds. It's different for every business, but having that right level of service in place is really important. Out of Betfair, we spun LMAX, where we decided we're going to build a financial exchange, but we're going to make it available on the internet. And the cool thing about having to do that was not just that we had to process those transactions really fast, we also had to work out the risk profile in real time to make sure, does somebody really have the money to be doing what they're going to do? And we did that in line with the transaction processing. So it was a really fun thing to do. But it kind of throwed up some really interesting contention problems. And if anybody's interested, come to my talk this afternoon. We're going to drill down into some of the problems and how you solve some of this. But we're talking in the orders of how do you do hundreds of thousands or millions of transactions a second and be sort of millisecond or even microsecond latency these days to do that. And these sort of things are possible. One of the things we ended up looking a lot at was SEDA, Stage Event-Driven Architecture. And in doing that, we could work out how to get really, really high throughput. But we discovered that we had really unpredictable latency, and that's no good. So it's no good being fast, but it takes a long time before you sort of get to giving the user an answer. And so this importance of latency become more and more of an issue. We discovered two major reasons for this. One was our approaches to concurrency. Most concurrency, where you've got concurrent access to a shared model, which is the business model, you end up with loads of queuing of facts, and this becomes a major throughput issue. We also had issues whereby you have to take that data and send it to multiple other nodes to be resilient. You've got to send it to disk. You start doing all of these different queues. The queues become the huge time involved, and this gives birth to the disruptor. So we ended up coming up with a disruptor as a result of trying to solve a number of problems. We wanted to avoid concurrency, and we wanted to make sure we can do multiple things in parallel and keep them coordinated without copying the data, without having to use locks, without passing to different queues. And the disruptor drove a lot of that. So a lot of people think, is the disruptor a better queue? Well, it's not really aimed at that. Its best usage is if you've got a graph of dependencies, like multiple things you want to have happen at a different time, and you want to bring them together to a synchronization point and get really good throughput and really low latency. That's where it fits quite well. So I kind of moved on from LMAX, and I've ended up helping people tune systems. And a lot of this I've found is coming down to how people do or do not understand modern hardware. And that's where I kind of come up with the Mechanical Sympathy blog. It's like trying to help people understand a little bit about how modern hardware works. And I spend a lot of time traveling, and I stand in queues like this all of the time. And it makes you really realize and appreciate queuing theory. And queuing theory is so key to so much of what we need to do and understanding what slows us down. We also have other laws that really matter. So who here's heard of Amdahl's law? Good for you. Who's heard of universal scalability law? A lot less. So Neil Gunther did a lot of field work where he was measuring systems going parallel, and what he discovered as a result of real-world measurements that Amdahl's law was a best-case scenario. In fact, you never even got close to it. He discovered that there was two major components to scale up. There's the contention in an algorithm, but also the coherence cost of making that data available to all parties participating in that algorithm. And this is what happens when you take an algorithm that is 95% parallel, so only 5% is the sequential component. You follow the blue line. You can't even get a 20x speed up with that. You add in 150 microseconds delay for coherence, which is pretty typical in a data center when you're doing parallel computing across a series of nodes. It starts slowing down because the coherence cost starts to dominate as the number of nodes goes up. And this ends up going backwards. And so it's a really bad model. If you have got contention and a coherence cost, you can't actually scale up. That's the formula for anybody who wants to go and look at it. Great piece of work by Neil Gunter that pulls out the work of Amdahl and takes it into the real world. What you start seeing from this is a first-class thing. So like mathematically you see this, but also you see it with working with the software, is any shared mutable state is evil. It will slow you down in ways that are horrible, and it will slow the team down because they'll spend most of the time chasing bugs. If you do concurrency on well-defined data structures like maps or queues or whatever, it's so easy for experts to even get this wrong. So if that is so easy to make mistakes on, how does anyone believe we can do a good job on a vague business model and put concurrency over the top of that when we barely even understand the business model, never mind the implications of concurrency on top of that? There's a kind of great quote from Paul Barnum where like once you've got a second computer, you can't have it till you've proven you know how to use the first one. And some of this comes out from a couple of really interesting papers that have been published this year. Like my version of it is even simpler. It's like you can't have the second CPU till you prove you've got the first one. And what's the grounding behind this? There's a paper called Cost. And what it was showing is that we've had lots of research comparing parallel algorithms and concurrent algorithms. And people are showing how one concurrent algorithm is faster than another concurrent algorithm, but they've fundamentally missed one thing out, and that's the control group of the single-threaded algorithm. The single-threaded baseline is if you're going to go parallel or concurrent, you must be getting benefits over the case of the single-threaded. And in a lot of their research is most of the parallel algorithms did not even come close to the performance of the single-threaded algorithm. So why are we going that way? So there is times when we need to, but we need to know when, and we need to know it against the right control group. I often find that rather than going wildly concurrent, is to break everything up into pipelines and have no concurrency within the pipeline itself. You hand off from one stage to another. The different stages are running concurrently and in parallel, and that gives you great throughput. If you look to nature, if you look to all our hardware work, pipelines is what's been shown to work really, really effectively. Also find that there's this interesting pattern where we deal with synchronous communication in distributed world because we think time doesn't exist. Well, time is one of those laws of physics that we cannot get away from. And if we pretend we can have truly synchronous actions in a distributed system, we limit our throughput massively. We really hurt our latency massively under load. And all of our algorithms slow down. So I started watching Breaking Bad a while ago, and that's kind of where the origin of this is. Because when you get into this sort of distributed programming, if you use synchronous-based communications, at the beginning it feels so easy. It feels so fast. It feels like I can make progress really, really quickly. But very soon you find it doesn't scale up. And I mean it doesn't scale up from a programming perspective, the complexities, the implications. The synchronous side makes you believe that you're not going to have problems, but yet those problems really do exist. If you go to a message passing approach and you treat everything as asynchronous, we can decouple in both space and time. And this decoupling can make life a whole lot easier. If anybody wants to ask me questions about this, come grab me afterwards. It's a subject I kind of care passionately about, and you need to spend a couple of hours on its own. But it enables pipeline. So once we've got messaging, we can pipeline, we can keep it really simple. And that's how those really, really fast platforms that were built in the finance and other spaces are done. They're all effectively pipelines, and they're all decoupled and totally asynchronous. So what's been happening with hardware? I find that many people think things like disk, memory, even SSDs are random access. They're not. Sorry to burst the illusion, but pretty much every storage means we have is tape. If you go through memory in a predictable fashion, it's much, much faster than if you go through it in a random fashion. You go to a hard disk and you hit it randomly with 4K pages versus going linearly. You find that linearly you'll get about 200 megabytes a second. Going randomly you'll get less than 1 megabyte a second. 200 times slower. That's not random in its behavior. Disks behave just like tape. And when you start getting into write behavior to SSDs, it sort of starts to happen again. And also, the latest research is showing they start to fail, they start having problems when you use them in a random write. Random read's different, but random write is an interesting problem. So go append only. It's the only real way to go. Networks is also something I find that people haven't realized have got so fast. Like I mentioned about how the finance space is driven forward. We're now down to the best networks are single-digit microseconds for a hop between two computers. This is way faster than you can even write to an SSD. It's about an order of magnitude faster than writing to an SSD. In fact, even if you have a pretty average network, it's still much faster. So quite often, if you want a resilient system, replicate to many machines rather than write to disk. If you think about it, writing to disk is just replicating to yourself in the future. So think about this. Comms is actually much, much faster than you think, and throughput is pretty phenomenal. The only problem in Java is we have to use NIO. And NIO can leave you feeling a bit unclean. So let's have a really simple example. I want to deal with lots of different sockets, and I want to do them asynchronously. So what I'll do is I'll select on a selector to see what work do I need to do. I'll then get a set of selection keys. I'll iterate over it. This is all very verbose, but what's actually hidden in here is a bit of a mess of locks and a lot of allocation. So you end up hurting the garbage collector, and you end up having a lot of lock contention. How about if rather than doing this sort of part of the algorithm, which is a kind of standout API design, and it's exactly that same mentality that I showed with string split. Change the code around and make it so that you can pass in the collection to be filled rather than return the collection. You can choose the data structure you want. Do a select now across the keys. Say what type you want as part of a query, and then iterate over the end of it. Okay, people will say, well, that's very kind of Java 8 and Lambda-ish. You could do this all right back to Java 1.1. This sort of design patterns is possible. It's been kind of done in lots of other programming languages. We need to learn from this. Like, to get the APIs right, we can get much, much better performance. Now, memory access, I've mentioned it. This is a kind of fun one. If we walk randomly all over our heaps, we really work against how our hardware tries to help us, because our hardware is trying to do three things for us from a bet perspective. It's trying to help us with the temporal bet, spatial bet, and pattern bet. Temporal means things that I've used recently I will use again in the near future. Spatial means things that are together are likely to be used together. And the pattern-based bet is that you're going to go with some predictable pattern through memory, either walk forwards or backwards, but not totally random. So taking that understanding, how could we build different data structures? So imagine if I could build a hash map, but I also had rarefied generics, and I could have arrays of structures. What could I do? Well, let's just look at how hash map works briefly. We have an array of buckets. We end up hashing a key. The key gives us a slot, and then from there, we put a node into the array at that point, and that's one key goes in. We do another key, same sort of thing, hashes to a different value, goes into a different bucket. We'll get another node hanging off that. I add a third one. This happens to have a collision. So you end up with the key needs to point off from the next to the previous in a little chain. We get a little linked list. But notice this, all of these arrows are pointers. These are all things where the CPU cannot help us with. They're called a data-dependent load. It doesn't know where to go till it knows the answer to what that value is. So what's the address of where I'm going to go to next? And it kind of lays out, this is kind of theoretical. It's not that there's big mistakes made here. This was designed a long time ago, and things have moved forward. So let's look at something else. Here's a different approach. This is what the .NET dictionary does, using the techniques that its language affords. Is it allocates an array of buckets. It also allocates an array to actually store the data itself as an array of structures. So I go to add my first element at this stage. I get a hash value. I put it at the top of the array of the actual data itself. I add a second one. It goes into the same data. I add a third one, and the third one has a collision, so it chains it with the next pointer. It's not actually even using pointers at this stage. But the real standout thing here is, look, all the data is together. It's all up in the same location. If I need to iterate, it's really fast because I can straight through memory. It's in the same operating system page. It's often in the same cache lines within the same page. Lots of things that our hardware needs to work with. What's the result of this? If you use a 2 gigabyte data set, you will typically be at least 10x faster with the .NET dictionary than you are with HashMap that comes with Java. And it's just a difference in design approach and making sure the language has the right features to get this. We could have these sorts of features in Java. Some of the work in value types gets us partially there, but we need much more than that. What I think we need to get the memory stuff right is 2 major things. We need the value types on the stack and be able to work on our stack well. From what I see profile in real-world applications, that's probably going to be about 30% of the way to where we could be compared to C. 70% is actually probably more in how we describe aggregates on the heap. And what do I mean by an aggregate? Well, when we model our objects, we tend to always say there's an association. But associations are more rich than that if you look at real modeling. Because if we just got a straight pointer, that's a straight association. Real modeling has got also aggregation and composition, where aggregation is saying this thing is used together. Keep it together for the benefits. Now, if you express that as a relationship, then the VM can honor that and help out. It can choose an implementation strategy whereby it keeps those things together. It can then use them together and dead reckon to them and work much better with the modern hardware. Object layout is a proposal that Gil Tene and I have put forward that we think will really help with this. So kind of to wrap up a little bit, I'm going to look at how culture has been evolving over this time. I love this picture particularly. If anybody is into astronomy, this was taken from the Hubble telescope pointed at the very darkest part of the sky. The very, very darkest part on a long exposure. What they discovered in this is in this one little picture, there's 3,000 galaxies. Each one of those has got 400 trillion stars in them on average. So it's just massive. What is kind of interesting to me is we're in a subject that's so massive as well. But we're kind of in the early days of it with computing. It's kind of like software alchemy. So we need to move forward. We're just still in this sort of era of working it out. So we shouldn't feel bad about the fact that we're making mistakes. We're kind of learning as we go. And I love how things from science has sort of come forward in other industries. Like, it's actually great being here in St. Petersburg with like the scientific history of them here. Like people like Mendeleev are part of your history here, which is superb. Like another great one being like Richard Feynman. But he talked about the pleasure of finding things out. Yes, we don't know all the answers, but it's actually fun to find it all out. It's a great time to be. We're in this sort of voids of discovery, working this out, working out how to do it better. Well, what can we do to do better? Well, let's learn from science. Let's measure as much as we can. Now, people will often talk about premature optimization. That's different from measurement. Knowing your ability is different from doing something about it. So like in all other engineering disciplines, you talk about engineering tolerance. If you're going to build a bridge, you know the torsional strength of steel, the compression strength of concrete. Knowing these things is useful, yet most developers don't know how much data they can send across a network connection. They don't know how much they can write to disk. They might have a vague idea of what the spec says, but what can they really get through the full stack and how it works? We've got to measure these things, and it's fun to know and do that. But very carefully, also take caution from this, guys. We all have biases. It is human nature to be biased, and we will look for certain patterns. In fact, you can give the same data to 2 different groups, and they will see different things in it. They want to see their own things. So we just have to be careful of that. We have to be aware and try and not make those mistakes. So we read the data, try to be open-minded, try to catch ourselves fitting the data to what we think it is. Because we will do it. We'll all do it and get it wrong at times, but kind of be aware of that. And so on that, I think I'm just about out of time, so I'm not sure I have time for any questions. If I have time for quick questions, I'll do that. If not, please catch me outside. And thank you very much for having me here.
Well, Thank you, Martin. I guess we don't have time for questions.
Thank you.